Hi guys, welcome to Investing with JYK. I'm a little sickly today, but so bear with me. And today we'll talk about 5G, especially around you know, radio and all that stuff. So it's not going to be specifically investing related, but it's going to affect. Um, it's basically how I drew the conclusion of some of the things that will drive my investing decisions. So what is 5G? 5G is the next generation mobile technology that our phones and all these IoT stuff will be using. The difference between 5G and 4G is that 5G claims to achieve a higher peak throughput in terms of data transfer rate and a lower latency. The benefit of a higher data transfer rate. I'm not using bandwidth because that will get confusing with the the RF term bandwidth. And um, the benefit of higher data transfer rate obviously is that you can transfer more data in the same time or spend less time transferring the same amount of data, and you can like watch high HD TVs and stuff. Um, and low latency is if you send a signal, you get a signal back. An example is now you can actually do like cloud computing for VR uh, uh, applications. So previously, if you wanted to do virtual reality things, you have to be using the phone. So the phone has limited battery, limited computation power, and all that stuff. And if you send it to the cloud, then the latency will kill you because there's two things. Latency will kill you because you get about 10 milliseconds in terms of latency, and then that round trip will get you 20 milliseconds, and that's before the server spends any time doing the computation. And so that basically means like generating the video and sending it back to you. Um, so that will, when you turn your head wearing the VR lens or whatever, if it is cloud-based at the current moment, if you use cellular network, you will get very dizzy very fast. Also, the um, resolution of the video that you see is going to be limited by the bandwidth. So the higher the bandwidth, the more pixels they can send to you. So those are the advantages, for example. And then there are other things, but the main claim is that you can get to about 20 gigabits per second and 1 millisecond in terms of latency. So about 100 times faster in data transfer rate, and then 1/10 the latency. Everything seems to be nicer. Okay, so how is that achieved? So they will be using different bands. There is a website called Global Mobile Suppliers Association. It looks fairly legit. They talk about how we'll use the 5G bands. You got the lower band, these are actually new 5G bands. They're fairly high. You will see why they're high later. I'll explain, but you can see they're 3 gigahertz plus, and then they have this higher bands. So these are 20 gigahertz, 25 gigahertz plus. And then you got these bands. So essentially, these are the traditional bands. The GSM, the 2G, 3G, 4G phones run at these bands. Okay, so why do they pick higher bands? So there's a thing called the Shannon theorem in information theory. What you got is there's a physical limit on how much data you can transfer, how many bits you can transfer given a channel's characteristics. So that is a physical limit. Obviously, um, at this, in any case, you will never breach it, but it's usually hard to reach it. Same goes, for example, the Carnot cycle with the internal combustion engine or heat engines, right? That gives you the maximum efficiency, but it's not what we can get usually. So it's dependent on the bandwidth of the channel. In this case, it's measured in hertz, so that's the size of the spectrum that you use. So if you use from 100 hertz to 110 hertz, your bandwidth will be 10 hertz. So that's the difference between the bottom frequency and the top frequency. And then the other thing is just signal to noise ratio. So that's the thing that you frequently see on speakers or something, as they say, I will have 100 decibels of signal to noise ratio. That just, it's the intensity of the signal versus intensity of the noise, but the decibels is going to be a logarithmic scale. So here they're just talking signal to noise in terms of linear power scale. Okay, so given that, we can actually compute the power. The bandwidth, the data transfer rate, the maximum data transfer rate. So there is a article in here that they said they were using some existing technology to do some data transfer, and they're using MIMO, massive MIMO actually, and then they're using a 20 megahertz channel. That's a fairly reasonable size channel that's typical for 4G. And so if you put that 20 megahertz in here, and so that's the bandwidth, and then if we use a signal to noise ratio of 1000, so that corresponds to 30 decibels. That's extremely good signal. There's this guy who runs some kind of website, but he published something, and you can actually validate it yourself. Right? So if you have your phone, you can actually see so I'm not sure if you can see this well, but let's see. Actually, no, you can't see this. It's too small. Anyways, you can check it with your phone. You can see that in terms of dBm, if you get around negative 100, you're already at low signal, and if you get negative 75, you're at really strong signal. So we're talking about 30 decibels. That's great signal. That's somewhere down in here, and really that's very rare. Very often we're down in the poor signal range, so we're looking at like 10 decibels. So for 10 decibels, that's just going to be something like I think that's just 10, I think. I have a calculator. So 10 decibels, that should just be 10. Yeah, that's exactly 10. Right, so if you put 10 decibels here, this is low quality, 20 megahertz, your maximum theoretical output is going to be 69 megabits per second. So divide by 8, which is a bit to byte, you end up with something like 8 megabytes per second, which is fairly reasonable if you think about it. If you, it's on the high side, and when you use a phone on a low low signal, when you have bad signal quality, your data transfer rate suffers. Right? Okay. So that's one thing. And if you really want a high transfer rate, this doesn't cut it for the 5G, what 5G promises us. So maybe you need 200 of those. So that just gives it 10x. So now you have 600. But in order to get to what they said, which is 20 gigabits, you are going to need some crazy high bandwidth here. So let's imagine now, we get even more, slightly better, 20, very good signal, 20 decibels, so that's 1,000. Actually, that's 100. 20 should be 100. Yeah, it's 100. So, you put a 100 here. And that gives you 1.3 gigabits per second. That's still not what they promised. So if you put another 0 here, you're at 13 gigabits, which still doesn't cut it. So you literally need 3 gigahertz in terms of the spectrum size to get the promised 20 gigabits per second that 5G says. So what does that mean? If you look at, look at these, where was I looking? Huh. That's odd. Can't find my thing. Oh, here. I know. Sorry. Oh, here. Oops. Yeah, if you think about these, right? If you need 3 gigahertz in terms of the difference between the minimum and the maximum frequency, you can't use any of these stuff. If you just start from 0 to all the way to 3 gigahertz, that just covers it, and that's a theoretical maximum. So you might need more than that. I'm not sure, but that's why they need higher frequencies, which also means that these frequencies won't be able to get you 20 gigabits. They might be able to get you, 1 to 2 gigabits, which is nothing to brush off. I mean, it's still really good, but those are theoretical numbers, remember. So you are going to basically, if you put 300 megahertz there, which is what they say is around 3 to 400 megahertz, right? And you can get about 2 gigabits per second at a really not extremely good, but fairly good signal to noise ratio. Okay, so that's one thing that we have to keep in mind. That's the reason we go high in the we have to go high in the band, in frequency, in order to have the space to fit these large bandwidths. And the second thing is, once you increase the system bandwidths, in order to keep the same signal-to-noise ratio, it's actually more difficult. There's a thing called a minimum detectable signal calculator. So if you just use 0.2 megahertz, you actually get the signal can be detected at negative 100 and negative 101 decibel watt, decibel milliwatt. So decibel milliwatt is just an absolute power power measure. So it can be converted into watts essentially. But the reason they put a dB here is that once you have dB here, dB is a logarithmic ratio. So now you can do computation arithmetic with dBs, right? So if you want a 20 if you want a 20 signal to noise ratio, you add 20 to here, that means you need to receive 100 dBm. So your phone needs to receive 100 dBm. Theoretically, that's the minimum in order for it to have a 20 decibel signal to noise ratio. So now if we increase it to 20 megahertz, so the noise figure, you can ignore this. This basically means what is the how much does your receiving equipment deteriorate, like make your signal noise ratio worse, right? So your equipment itself will introduce some noise into it. So let's say 20 megahertz, which was what the Sprint people were using. So at that point, you need 100 and 100 and 1 decibel milliwatt in order to be detected. And then if you at that point, if you give it a 20 decibel, you end up with negative 80 dBm. And in this case, we discovered they need 3,000 megahertz in order to transfer, in order to get the in order to get the 20 gigabits per second transfer rate. So now you see that the required dBm is now negative 80, right? And then tack on the 20 dB difference for the signal to noise ratio. This is basic noise. Signal to noise ratio, you're looking at 60. So you need negative 60 dBm in order to get detected, in order to get a good enough signal. So you can see that's here. You need to be at high signal, basically, all the way in here. So if you think about it, what this means is in order to transfer more data, you need more bandwidth. Given more bandwidth, the inherent noise of the channel goes up. And this inherent thing also depends on the temperature, but it calculated in Kelvin, so it doesn't change too much because we're at like 300 Kelvin something. So it goes up by 10 degrees C, you're at 3% really. So that doesn't matter too much. If it goes up by 100, you're dead. So, okay. So yeah, so the more data we need to push through, the higher the bandwidth in terms of the spectrum we need to use, which drives up the minimum detectable signal. So that means you need even more absolute power, imagine dBm, at your phone, right? So remember that. And then also because of the fact that we need more bandwidth, we need to find a space in the spectrum, because the spectrum is shared with everybody else. The lower ones are all being used by like radio, FM something. The FM is like 100-ish, 90 something. You have the FM down there, you have the radars, you have whatever military use, you have the all kinds of crap at the low end. So you kind of have to, and you can't take 3 gigahertz at the low end because that just drowns out everybody else. So now you have to move it up. So now we're at like 20, 30 gigahertz. So one problem with that is absorption. So I checked here, extremely high frequency. So those are 30 to 300 gigahertz. It's just a name. It's not. We call it millimeter waves. So it's just a wave. It's part of the. So if you look at, actually, there's another one that you have the super high frequency, which is 3 to 300 gigahertz. So that's where, I guess that could also be where we're looking at for 5G. That's what we'll be using. And this stuff gets absorbed by water a lot more and air a lot more than lower frequency ones. So in order to find that, I actually dug through a shit ton of stuff. So I found this nice thing which says, as the wavelength increases, which is when the frequency decreases, at very low frequencies, the atmosphere is opaque. So essentially, you can't transmit anything. And there's this weird window here where for some reason nothing is absorbing these radio waves. And you can see it kind of just dies at the millimeter level, right? So as you go down from 1 centimeter, uh, so that corresponds to 3 gigahertz. So this is probably something like 2 or 2 gigahertz ish. Since it's logarithmic, right? So this would be like 300 megahertz. So you can see that between, like, there's a huge hole here where nothing really gets absorbed. So these are the frequency bands of 700, 800, 900, these things, up to like 1 gigahertz-ish. But after that, you got this quick fall off at up to 3 gigahertz. And then it comes back a little bit, and then it drops off to almost nothing. Right, so that's fairly interesting, but it's not very accurate. So I can't get numbers out of this. It says transparency, but okay. So then I looked into how water can absorb things, but this is talking about like these are really high frequencies, basically, like terahertz. So I was thinking maybe this is talking about the vibration of different atoms and stuff. So atoms and electrons and the bonds and all that things. So I was like, probably doesn't help me. Then I came across this paper that talks about how water absorbs how water absorbs things. Water vapor absorb things, but it goes up to 800 gigahertz, so the range is too high, probably doesn't match. I kept on digging until I found this beauty. So this is from the International Telecommunications Union, and I found that they have this nice graph that shows specific attenuation for atmospheric gases with both basically oxygen and mostly it's oxygen and water. And they have this graph, and then they also have a way to compute it. I put that into Excel. That's one thing. The other part I realized that I've read somewhere that rain actually absorbs a lot of signal when the frequency goes high. So then I found from same organization, they have some constants, right? They have some constants, and then a formula for calculating specific attenuation, estimating. So I put that in this Excel thing. So I jot down these numbers. This one I just took off the graph. The rain one I computed using the numbers that they provide, and then the formula they provide, and then I put some characteristic range. You got light, moderate, heavy, and some stuff. That's millimeter per hour. So in an hour, how much rain would have collected if the whole thing is flat. And then the way I got this is by looking at here, this Cumulus Wiki. And apparently you got these numbers, so I basically took the middle number for each of these rains. And for extreme rain, I just put 100. And actually that's not very rare, because I was reading this, there was some rain rate comparison, and then they said, oh, there are rain rates that's more than 120 millimeters an hour. So that's probably hurricane. But you do want your phone to keep working in a hurricane. Maybe you want to call somebody, right? You want data in a hurricane. So then I put everything in numbers, and then so this is characteristic for uh, uh, for um, uh, what do you call this? The current 3G, 4G things, the strong signal ones, 700, 800, 900, and then you got then 1900, 1800, 2.1, something like that. This one, between these two, is going to be the new 5G, the lower band part. And this is the one that's supposed to give us the fast transfer of 20 gigabits per second. And immediately you can notice at 10 kilometers, you're looking at simply from attenuation, not even the spreading out of the signal. Right? So that would have its own effect. That's the same for every single frequency. But simply looking at the attenuation, you're losing 22 decibels. And that is fairly crazy in a heavy rain. So I put heavy rain. Right? So if you put extreme rain, there is no way you can get any signal. Not just that, your rain attenuation, you can see this is quite crazy actually. The rain attenuation just goes through the roof. The gas attenuation goes to 0.1, so over 10 kilometers you might lose 1 decibel, which is okay. But by the time you get to rain, then you lose like 19 decibels per kilometer. And remember, remember the this thing here, signal. This is basic signal to noise ratio. Right? So that is enough to turn great signal minus 19 down to low signal, and anything medium down to nothing. And yeah, so and at 10 kilometers, you basically have nothing, no signal, like whatsoever, anywhere. So there are, there's a channel called the Investing with Sven or something. I think Sven PhD, Sven Carlin PhD. Yeah, so I like his channel, but he once came up with a video saying that it is possible to replace the actual cable with 5G because 5G has such great transfer rate. But looking at this, it's never going to replace the cable because people want reliable communication even in a hurricane. If the hurricane comes and all my communication dies, that's not exactly what I want. And if a hurricane comes and all of a sudden my communication becomes much slower, and yeah, so even if you have moderate rain, you still get pretty shitty signal deterioration at 10 kilometers. So that's the typical cell density in rural areas. So 6 is pretty big because 6 goes basically, that's 1 bar down. That's basically just 1 bar down. Simply with a moderate amount of rain. So yeah. So what does that mean for us? So in terms of investing, right? So obviously people will demand the quick speed. They will probably not reach the maximum 20 gigabit per second, but maybe they still want 5. And for 5 gigabit per second, you do need these pretty high frequencies. And the only way you can overcome the whole attenuation problem is by putting more cell towers. So so that just means there will be a lot more demand for cell towers. Maybe instead of every 10 kilometers, you need one every 1 kilometer. And yeah, so that's one thing. And secondly, we're just looking at open space here, and this is with line of sight essentially. And rain blocks visible light, but also blocks the microwave or millimeter waves. And the same 30 gigahertz or more wave will get blocked by structures such as the drywall or wood, not mentioned metal, much more than the lower frequency ones. So that means for 5G, in order to reap the benefit, the capital expenditure will be a lot more than 4G, a shit ton more. You will need one cell tower probably per, I don't know, one cell tower per, no longer per neighborhood, but maybe per every 3-4 houses you would need one. If you were to get the really high speeds. Obviously, if you just want to get 4G times 2 speeds, yeah, you can use these frequencies, 3 and 4 gigahertz bands. That will get you for sure, 500 megabits or 600 megabits per second. This is fairly good, but these already they already demonstrate a fair bit of penetration problems, because if you ever used a Wi-Fi router, if you turn on a 2.4 and 5 gigahertz, the 5 gigahertz gives you a much faster transfer rate, simply because they actually is a wider band. It's like 4.8 to 5.2 or something. I don't remember. And but if you stay behind a wall, the 2.4 is signals are going to be much stronger than the 5. And same thing is going to happen here, going from 700 megahertz to close to 4 gigahertz. The absorption by different materials is just going to become much stronger. People say, yeah, but higher frequency waves have more energy. Why this? I don't exactly know. I'm guessing it has something to do with the ability to excite different particles. So when you're really low energy, you kind of just move by without, it's almost like if you had a big block and you hit it with something in a fairly elastic way. You hit it, and if you're very small, you don't have much energy, you retain. So this whole thing doesn't move. You retain most of the speed and velocity going back. But if it's almost like momentum, right? So if you are similar in size, or if you are very you're carrying a lot of energy, then much of that will be absorbed by this big stuff. So in this case, it's like photons hitting maybe electrons. So electrons may have a certain mass and they have certain bonding energy, but when it gets hit and it doesn't really move, all that energy gets retained by the photon, so that keeps going. I'm guessing that's how it works, but I don't know exactly. And let me know where I can find that. I've always been very curious why that is the case. This is just an explanation I came up with. So yeah, so that's a lot of towers that we need, and maybe we'll even have like tiny, 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 tiny cells um, that are per office. It's almost like Wi-Fi routers uh, instead of what we now know as cell phone towers, because you frequently see these gigantic cell phone towers just rising up with a bunch of antenna and stuff on top. But maybe those will go away, and or there'll be a lot more of those. They will transmit less power, but there will be a bunch more of them. Okay, so that means that I got interested in these guys, these tower people. Yay! American Tower, Castle, Crown Castle, and whatever this SBA Communications. And that also means since we now need a lot more cell towers, um, the capital expenditure is going to be much higher for telecommunication people. So their costs just went up. So AT&T and Verizon, these guys, they probably really don't like 5G, but because they can't really charge you that much more, right? But they kind of have to do it because it's a prisoner's dilemma. If you don't do it, someone else does it and steals all your customer, and you're dead. So they kind of are forced into this. It's the beauty of capitalism or competition, I would say. And so that's bad for them. But on the other hand, because of all that capex, um, at least for American Tower or these cell phone tower owners, they should earn a decent amount. Also, whoever manufactures these devices, the antennas, the signal processing devices, and all that, the base stations themselves, these guys should benefit a lot. I'm yet to find these investments, but I will take a look in the future. And yeah, that'll be for today. I'm sorry today is not, you know, exactly investment related. I just want to share like how I go about estimating um, how much more demand there will be, and also it's also just interesting curiosity, I guess. Yeah, and I'm not a RF person. I probably got a bunch of this wrong. So if you know, um, if you see anything that I got wrong, please let me know. And also, if you know someone that might be able to point out my mistakes, please share the video with them and leave a comment. Tell me how I'm wrong, and I thank you in advance. Yeah. See you next time. We'll talk probably just about American Tower.